Okay, so these will be a few comments on the force acting on a moving charge. So this will be the magnetic force acting on an electric charge that's moving inside a magnetic field. And I'm going to go through a few examples of how to use the right-hand rule for this particular problem. So the essential story is the following. Imagine we have a magnetic field. Let's say it's represented by this pattern where the field is pointing out of the picture, and so this would represent the magnetic field B, and then a charge with a velocity v. Let's assume for the moment it's a positive charge, comes in this direction. This would be the direction of the velocity vector. As a result of this, the charge will experience a force, which I'll show in blue, and in this case, the force happens to be pointing downward, and we'll go through a few examples to explain how that works. Okay, so the equation that describes this can be written this way. It's F equals Q with whatever the charge is, multiplied by the velocity times the magnetic field. Uh, if we if you look at uh, the details of that expression, we can say that when we write the force this way, F equals QV times B, that the magnitude of the force is going to be given by the magnitude of the charge, so that if it's a negative charge, we ignore the negative sign, times the magnitude of the velocity vector, times the magnitude of the magnetic field vector, times the sine of the angle theta, where theta is the angle between v, the velocity, and b, the magnetic field. So this will be what theta is, between the angle between v and b. And I'm going to focus mostly on the direction of the magnetic force. So for the direction, we're going to use the right-hand rule. Okay, so I'm going to just abbreviate this right-hand rule. Of course, if we have a negative charge, it'll be a slightly different possibility, and I'm going to go through that as well. So let's go to an example here where we have, say, a charge moving to the right. So in this picture, I'm going to assume that the velocity, let's take it in red. So the velocity vector is going to be given by the thumb. So this will be the velocity vector. And the magnetic field vector would be the fingers. So if we put that in green, the fingers would represent the B vector going this way. And as a result of this, there is a magnetic force, which I'll show here in blue. So with the right-hand rule, the palm of the hand facing us means that the force is going to point out of the picture, and we would get this. Now, in this particular example, I'm assuming that the velocity vector and the magnetic field vector make an angle of 90 degrees, but that's not really necessary. It could be any other angle, so you could have, say, the velocity vector going this way and the field at a slightly different angle than 90. So, for instance, the field could be pointing this way, and would still have the force vector perpendicular to both of these, and so it'd still be pointing out in this direction. Okay, so, and then in this case, as I said earlier, for the force, for the magnitude of the force, if I drop all the signs, so this implies the magnitude and V and B, so I'm using here the notation without the vectors to represent the magnitudes of V and B. This assumes, as I said earlier, that this is a positive charge. And so for a positive charge, you would use the right hand. Okay? So this here works for a positive charge. Let's take another example of the same thing. So let's go to another example of this. So in this picture, I have the position of the vectors in a different way. So the thumb always represents the velocity. So let's keep that in red. The velocity vector goes this way. So we have this. The B field is this time pointing to the left. So if we show it again, the field is going to point that way. The fingers show the direction of the field. And because I'm using the right hand, I'm assuming this is a positive charge. So when this is done saving, okay, now I can switch to blue. So this is the a right hand, and that's because I'm assuming the charge is positive. Then the force is going to come out of the picture. So V cross B is going to give me a force pointing in this direction. So here's a force for this case. I forget to label the magnetic field, so the B field is in this direction. So this would be the case for this particular position. What if we had another position, let's say something like this, where the vectors are again in a different position. So we could have, in this case, the velocity vector would point straight up. So this would be the velocity vector. And the field is now pointing to the right. So the B field is going to point in this direction. And for this case, the charge is still positive. It's still a right-hand rule. So it's still a right-hand rule, and we're still using a positive Q. And so the force in this case would be with the palm facing inward. I would show it this way. The force would have to go in, and this is the force I would get. And the magnitude of force would be the same as all in the other cases. All right, so now let's consider another example where we go for a negative charge. So this will be for a negative charge. So I'm going to change colors for the force, but let's begin with the direction of the velocity. So the thumb is still the velocity vector, so it goes this way. So this is velocity. The B field is pointing to the right. Those are the fingers pointing this way. So here's B. And as I said, this will be an example of using this for a negative charge. So with a negative charge, I'm going to use the left hand. So negative Q, so I use the left hand for this. And in this case, the palm of the hand is facing us. So here's the direction of the force. It's going to come out to the picture in this case. Now for the magnitude of the force, we'd still be using the magnitude of F as whatever the magnitude of the charge, so we drop the negative sign, times the magnitude of B, of the velocity, times the magnitude of B, and of course the sine of the angle between the velocity and the magnetic field. So right now with the hands positioned this way, this would be a 90-degree angle, but we could also have a case where the velocity is pointing this way. The magnetic field could be at any other angle, but let's say the field is going this way. So now the angle between those two vectors would be less than 90, but still some angle, and the force would still be, in this case, pointing out if the charge is negative. So this will be an example of using the left hand for a negative charge. Let's take a look at another example, again, for a negative charge. So if we go here, we would have this time the velocity vector pointing to the left. So here's the velocity vector going this way. So the charge is heading to the left. And then we put it inside a magnetic field that is pointing straight up. That's the fingers going this way. Here's B. And so for a negative charge, we would get this time a force vector that is going to come out. The palm of the hand is pointing out, so we would make the usual symbol for an outgoing vector or outward vector, and it point in this direction. And then let's take one more example of this. And let's see here, I have another example where this time the the B field is pointing up. So let's go through the same procedure. Velocity first, so the thumb is pointing this way. Here's the velocity vector. The fingers are pointing up. That's the magnetic field. So the magnetic field is going to go in this direction. And because we're using the left hand, you can see the palm facing inward. And so in this case, the force is going to be inward and point in this direction. Okay, so now let's see. I want to go over a couple of details about the way this affects the charge. So I'm going to go back to an example of a positive charge moving inside a magnetic field. So let's assume that we have a positive charge moving in this direction, velocity going this way, inside a magnetic field that I'm going to count as coming out. And I'm going to assume that this is a uniform magnetic field, meaning it's the same magnetic field everywhere. And so the entire region here has one value for the magnetic field. So because of that, the charge, with the charge being positive, is going to experience a force pointing it, pushing it to the right. So going this way. So we'll wait for this. Okay, I think it's going to work. So here's the force vector, and because the charge is going to be subjected to the same force, then it will change direction, and eventually it will follow a path that will be a circular path if we assume that the field is filling up the entire space. And no matter where the charge is, the force is always going to point inward, and that is indicative of what we learned about in Physics 1, which was a centripetal force. So in this case, the magnetic force happens to be a centripetal force. So we have two things we can say about this. I'm assuming, by the way, that the angle between the velocity and the B field is 90 degrees. So if I focus on the magnitude of the force, it will be equal to QVB. In this case, the sine of theta is equal to 1. So I can simplify this. And then if you remember from Physics 1, this will be also mv squared over r, where r is the radius of the circle. So this would be this radius here. So if we put those two things together, we end up with the following relationship. So we would have QVB equal to mv squared over r, which when we solve, for instance, for r, tells us that r will be equal to mv over qb. So the radius of the circle will be dependent on the mass, the velocity, the charge, and the magnetic field. And you can see how each of these factors is going to affect the radius. For instance, if m increases, r increases. On the other hand, if q increases, r decreases. So you can just look at that equation and you can see how those things affect the radius. Also, for instance, if the magnitude of velocity increases, so does the radius. It's directly proportional. Okay. Another interesting thing we can talk about when the charge is moving on this circle, so here's the radius r, we can ask a question about how long does it take for the charge to go around once, and that's called a period. So the period is labeled capital T, and it would be the time to go around once. So going around once would be the circumference of the circle, so it would be 2 pi times the radius. And then, of course, divided by the velocity, this will give us the period. But we can express the velocity in terms of the radius, or the radius in terms of the velocity. We can do it either way. So, for instance, if I use what we just came up with for the radius, here's what we can write for the period. So the period can be 2 pi times that expression, which was mv over qb. That's for r. And then we divide this by the velocity, so you can see how the velocity cancels, and we end up with 2 pi m over q times b. We can process this a little further. One of the interesting quantities for this kind of motion is the frequency. So the frequency is defined as let's write this here. So the frequency is defined as the inverse of the period. So if we invert that equation right there, we can say that it's going to be equal to qb over 2 pi m. And then we can also introduce something called, so before I go further, this is what's called the frequency. And there is something else, another quantity called the angular frequency. And the angular frequency is defined in terms of the frequency as omega equals 2 pi times the frequency. So if you combine those pieces, you end up with omega equal to 2 pi times the frequency, which, as you see here, is QB over 2 pi m, where m is a mass, and you can see the 2 pi cancels. And so the angular frequency will then depend only on q, b, and m. The velocity is not relevant for this. So this is the important idea, that this is independent of v. So no matter how fast the charges are, the frequency is always the same. And this particular quantity here, well, this is called the angular frequency, but this particular frequency is known as a cyclotron frequency. And your textbook has a few details about the historical importance of this cyclotron frequency, but I just wanted to point out how we get it and the fact that it's independent of the velocity, which is sometimes a little surprising because no matter how fast the charge is, if you ask for the angular frequency, you get the same result no matter what. And like, for instance, if you look at the period, I'm sorry, I meant also the same thing happens with a period. If you take a look at the period, you'll notice that the velocity is not present here. So here's another observation. Let me put it in red here, that this does not depend on the velocity. So what that means is that given charges inside a magnetic field, it doesn't matter what their velocity is, it's the mass and the charge of the charge that will determine how long it will take to complete one cycle. Okay, so I think this is what I wanted to add to this discussion, but I don't think we get enough time in class to go over some of these details. Hopefully this will be helpful.